It's kind of crazy to think about, but our modern cars, they're basically turning into supercomputers on wheels. They're just gulping down this massive flood of data every single second. But here's the kicker. What happens when even that isn't fast enough? So let's get right to the heart of it. Can a self-driving car, all by itself, really truly think fast enough to make one of those life-or-death decisions, in the blink of an eye? Well, the short answer is nope, not always. To nail that critical split-second decision, the car's own brain needs a little help. It needs an extension, really. And that help comes from the edge of the network. In that idea right there, that brings us to the core of what we're talking about today. It's a technology called vehicular edge computing, or, VEC for short. Okay, so the basic idea is actually pretty straightforward. A car can offload its heaviest, most complex computing tasks to these nearby servers. They're called roadside units, or RSUs. Seriously, just picture it. It's like your car gets a temporary super fast brain boost from a little computer hiding on the nearest lamppost. Kind of cool, right? So what is VEC, really? Well, at its heart, it's a system that lets cars wirelessly shoot off those really intense computational jobs to a server that's close by. And why do this? Well, the whole point is to slash latency, that critical delay in processing time. And on top of that, it saves the car's battery. And of course, the big one, it makes everything a whole lot safer. But, as clean and elegant as that sounds, it's not that simple. There are some major real-world roadblocks. So let's get into the messy part and see why VEC is actually way harder to pull off than it sounds. Okay, challenge number 1. It's a classic, limited resources. These roadside units, they're not some magical infinite cloud server farm. They've got a set amount of bandwidth, a set amount of processing power, and every single car buzzing around has to share that same small pie. All right, challenge number 2, the insane need for speed. We're talking about critical tasks, right? Like spotting a pedestrian who just stepped off the curb. That decision has to be made and sent back in as little as 10 milliseconds. That is literally faster than you can blink. There is zero room for error, zero room for delay. And finally, we've got the biggest wild card of them all. Everything is always moving. Cars are constantly in motion, and that means the wireless connection to that roadside unit, it's all over the place. It's changing constantly, super fast, and in ways you just can't predict. You could have a perfect, rock-solid 5G signal one second, and the next, it's practically gone. So, with all those problems, how do you even begin to solve this puzzle? Well, a couple of researchers, Chuan Xiaogao and Arvind Iswaran, came up with a really clever two-part breakthrough. And the first piece of that puzzle is a much smarter way to hand out those limited resources. To really get why their solution is so cool, you gotta look at the old ways of doing things. It's kind of like the classic tortoise and the hare story. So on one side, you've got what are called optimal algorithms. These are the tortoises. They are meticulous, they will find the absolute perfect solution, but they're so slow. There's no way they're meeting a 10 millisecond deadline. Then you've got the heuristic algorithms. These guys are the hares. They're blazing fast, but they're kind of just winging it. They're taking shortcuts, which means there's absolutely no guarantee that their answer is even a good one. And that's exactly where their new algorithm called SAR-Round comes into play. It's built from the ground up to find that perfect sweet spot, balancing the need for speed with the need for a quality answer. The goal is simple: find a really good solution and find it really fast. Okay, but how much better is it really? Let's talk numbers. The best algorithm before this could only guarantee a solution that was, at a minimum, 1/6 as good as the absolute perfect tortoise solution. What Sauron does is it boosts that guarantee all the way up to 1/4. It literally raises the minimum standard, the performance floor. Now, I know what you're thinking. Going from 1/6 to 1/4, it might not sound like a huge deal, but let's put that into perspective for a second. That is a 50% improvement in the guaranteed minimum performance. And in a system like this, where we're talking about split-second decisions and people's safety, that is a massive leap forward in reliability. All right, so that takes care of the resource problem. But what about that other big headache? The constant motion, the unstable connections. Well, that brings us to the second part of their breakthrough, a system designed specifically to adapt to constant change. What they built is something they call an online control framework. The best way to think about it is like a very careful, very organized digital handshake. So, step 1, a car sends a service request. Step 2,
A scheduler, using that smart surround algorithm, assigns the resources. Step 3, the roadside unit gets everything prepped and ready to go. And here's the crucial part. Only when everything is perfectly lined up does the vehicle get the final go signal, an offload grant, to start its task. The genius of this is that it takes all that setup time out of that precious 10-millisecond crunch time.
Okay, that's a fantastic system for getting things started. But I bet you're wondering the same thing I was. What happens if that 5G signal just tanks right in the middle of a super important job? And this is the really brilliant part. The whole framework is designed to constantly adapt. I'm talking every few milliseconds, the vehicles are sending these tiny little updates on their signal strength back to the RSU. The RSU is constantly crunching this data, recalculating. Can we still meet the deadline? Yes? No? And if the signal starts to degrade, the system can react instantly. It can shift resources around or even tell the car, hey, you're on your own for a second, handle this one locally. It all happens on the fly, ensuring the system never misses a beat.
So all this sounds great in theory, right? But the real question is, does it actually work in practice? Well, to prove it, the researchers didn't just write a paper. They built an entire virtual city. They built a custom simulator from scratch called Vexim, and they did not mess around with making it realistic. They fed it real-world GPS data from 80 actual taxis driving around a 1-by-1 kilometer chunk of Shanghai. They modeled in 15 roadside units and gave the virtual cars real jobs to do, tasks based on actual AI object detection applications. This was a serious stress test.
So the big moment. What did they find? Well, let's just look at one of the key results. How much energy the cars saved. And this chart, well, it speaks for itself. That bar on the far left, that's surround. It's not even close. It consistently outperformed every single one of the other cutting-edge algorithms they threw at it.
You don't even have to take my word for it. The researchers summed it up perfectly in their own paper. They said, and I'm quoting here, Sauron consistently outperforms all benchmark algorithms, demonstrating its superior resource utilization efficiency. It's hard to be clearer than that. So what all this really shows is just how far this technology is coming along. We're finding these incredibly clever ways for the network around our cars to think faster, smarter, and more reliably. Which kind of leaves us with one big final question, right? Now that the network can keep up, what's the next major hurdle we have to get over to really unlock that fully autonomous future we're all waiting for?